Okay, let's get started, please. Today we're going to talk about limits and infinity. Limits and infinity. Okay, we're going to start off with limits and infinity, and then we're going to go on into the chapter about differentiation. So let's recall what it means if we're just talking about finite limits. So you have some function, and the limit of that function is q as x approaches p. Can somebody give me like an epsilon-delta definition? What does this mean? Does anybody recall the epsilon-delta definition? Anybody who wants to pass the course? The definition? Max?
For any neighborhood of radius epsilon around q, there's a neighborhood of radius delta around p such that the p neighborhood is mapped to some subset of the q neighborhood.
Okay, good. So it says, it's like this. Somebody, no matter what epsilon neighborhood you're given, so somebody gives you an epsilon neighborhood here, right? No matter what epsilon neighborhood you're given, there is a delta neighborhood such that the punctured delta neighborhood, remember, the punctured delta neighborhood gets mapped inside of the epsilon neighborhood. Right? So in symbols, right, for all epsilon bigger than 0, they exist for delta bigger than 0, such that f of the punctured delta neighborhood of p gets mapped inside of the epsilon neighborhood of q. Right. So that was the definition, right? The definition of this. Okay. So, yeah, Max.
Do you need to specify that delta is greater than 0 since it's the punctured neighborhood?
Well, we do just because we want it to be a radius, right? We want it to be a radius. This doesn't make sense for negative numbers, so we specify it. Okay. Oh yeah, all right.
I think we sometimes had like the delta neighborhood intersect E.
Yeah, yeah. So I'm just ignoring it right now. So yes, it's true. If f is some function, from, so you've got, to make it more complete, you've got two metric spaces. You've got two metric spaces. You've got a subset of the metric space, and you've got this domain of f, right? So yeah. So properly, I should put that in. Properly, I should put that in. But right now, I'm just gonna ignore it. So let's just pretend. I'm pretending that f is defined on the whole space. Okay, just for simplicity. But yeah, you're right. I should probably say that. Okay, so we're gonna talk about what it means for a limit. To talk what we mean by the limit of f of x as x goes to infinity being something. Okay. Okay. So we're in yeah. Okay. So okay. So it's going to be something similar. Okay. It's going to be something similar. You have something like this. F. So you have some point Q. Okay. You have some point Q, and you want to know what it means to say that as x goes to infinity, the limit goes to Q. Okay. So let me draw like sort of like the normal picture, and then I'll split it up sideways. Okay. So here is your Q, right? And your values are getting closer and closer to Q as x goes out towards infinity, right? That's sort of your standard picture. Okay. So let's think of what we can say in terms of epsilons and deltas now, right? What we're saying is that how we're going to change the definitions like this. We'll say, okay, given any epsilon, q plus epsilon, q minus epsilon, what are we going to say? Well, we'll say that there's some point, there's some time c, and past that time c, everybody's within the neighborhood, right? So there's some time c past which everybody is in the neighborhood, right? So let me write it out. And given any epsilon greater than 0, there exists a c such that if x is bigger than c, then f of x minus q, the distance between f of x and q, right? The distance between f of x and q is smaller than epsilon. Okay. Yeah, Lana.
So why don't we define C as like, or why don't we involve like delta neighborhood of C as we did for like corner cases?
Yeah, well, you see, what we would like to have is a delta neighborhood of infinity.
Yeah.
Right? We want a delta neighborhood of infinity. Right? That would be the appropriate thing. Right? So infinity is over here. Right? Infinity you think of as being over there. We want a neighborhood of infinity. And what our neighborhood of infinity is this. Right? Everything past C. Okay. So that's the analog of the neighborhood of infinity. A point past which, right? An open interval from C to infinity. Okay, so let me write it that way. Right? We say, okay, so here's the definition. You have some function on the real line going into some metric space Y. Y, a metric space. The limit of f of x as x approaches infinity is q, means that for all neighborhoods of q, epsilon greater than 0, there exists a an open interval at c infinity such that f of c infinity is contained in the epsilon neighborhood of q. Okay, so the picture you want to have in your head is like this, right? Here's your metric space Y. Here is your R, right? And here's your function. And Q is in Y, right? Q is in Y, right? And we're saying that the limit is Q as x goes to infinity, means that if somebody says, I want you to stay within epsilon of Q, then you can find some C above which everything gets mapped inside there, right? Some C past which everything gets mapped inside there, right? And if somebody wants you to stay closer, there's some other C above which everything gets mapped inside there. Okay. Yeah, Dayan.
Is there a reason that we don't consider other metric spaces that are totally ordered?
Like?
As the domain.
Like, could we do this for some other? Yeah, we could. I don't think so. You could do something like this. Yeah. Yeah. Okay. Okay. So. Okay. So I'm just wondering if we should go on, or should we talk more about this? I think let's go on. Okay, let's go on to the section on differentiation, because that's more entertaining, and I think might even be more fun for the visitors. Well, actually, just for your amusement, so in the real line, we don't think of infinity as being a point, right? But if you take a course in complex analysis, there actually is an infinity. It's a very definite thing. Who's taken complex analysis before? What? Nobody?
This is a prerequisite.
No, it's not a prerequisite.
Wait, it's all prerequisite.
I think this is a prerequisite for complex analysis. So it's, it'd be.
That should be reversed.
Yeah. Okay. Well, in complex analysis, one thing that you do is you've got the so this is just for your entertainment. Okay. So you have the complex plane, and one thing that people do is actually something called stereographic projection. So you take there are two ways of doing it, but let me say it this way. Yeah. So you take a unit sphere and you set it down at the origin. Okay. And what you do is you say, well, I'm going to think of the complex plane as this sphere by identifying points on the plane with points on the sphere. Okay. And the way I'm going to do it is I'm going to have this north pole here, and I'm going to take this point, and I'm going to draw a line. Whatever point I have on the complex plane, I'm going to draw a line and to that north pole. But at some point, it's going to intersect the sphere, right? At some point, it's going to hit the sphere. Let's call that point, we identify those 2 points. So every point on the plane gets identified with a point on the sphere, right? So if you look at the complex plane, what gets mapped onto, it gets sort of mapped onto this sphere, except for one point. What point is missing? The north pole, right? The north pole, right? And so further, you see that as you go farther and farther out, as your numbers grow greater in magnitude, what do they get closer to? Well, they get closer to this north pole thing, right? But they never reach it, right? They never reach it. So it makes sense to call this thing infinity, right? And so you put in infinity, you compactify the sphere, right? And you get this thing called the Riemann sphere that you use in complex analysis. Just for amusement. So yeah, so if people ask you, what is infinity? Well, you just say it's the north pole. Okay, yeah, maybe someday I'll get to teach a class in complex analysis. Okay, so let's go on. Chapter 5, differentiation. Okay, so good. Okay, so let's. Okay, somebody tell me what differentiation means. So you have some function, let's say, on a unit on a closed and bounded interval. Then how do we define the derivative? How do we define the derivative? I want one of the people visiting to define the derivative. Does somebody want to define the derivative? Anybody? Yes.
The slope of a line tangent to a point on the graph.
Okay, slope of the line tangent to the point on the graph. And how do you get that slope of the tangent line?
Use the derivative formula.
Use a derivative formula?
It's
sounds
like
a little circular.
2 points.
Yes.
The secant line that get increasing.
Yes,
closer
exactly.
together.
Right? So you say, okay, you got this thing, right? You're taking the derivative at some point. What you do is you take a second point, right? You take a second point t, and you look at the slope of the line between those 2 points, right? Well, the slope of that line is going to be f of t minus f of x over t minus x, right? And then you let the second point approach the first point, and that'll give you the slope of the tangent line, right? So so you get a bonus point on the next example. If f of t minus f of x over t minus x as t approaches x exists, we call that number, we call that limit f prime x, right? And say f is differentiable at x, right? F is differentiable at x. The derivative of f at x is that value. Okay. Okay. So it will be useful, it's profitable, let's say, to think as follows. Right? F differentiable at x means that there exists some number. There exists a number f of x, f prime x. This backwards e means there exists. Okay. So there exists some number f prime of x such that the limit of f of t minus f of x over t minus x equals f prime x. That's the same thing I just said. So why am I saying that? Okay. So this is the definition you have, right? Differentiable means that there's some number that has this property, right? Not surprising. Let's change it. That's the same thing as saying that this over that minus f prime x equals 0. Again, you should be like, why is he making such minor changes, right? Okay, so I've said the same thing again, right? This is the same thing as being differentiable. There's some number such that this happens, right? Okay, let's call this thing u of t. Call this thing u of t. So another way of saying this is saying that there exists some f prime x and function u of t such that f of t minus f of x over t minus x equals f prime x plus u of t. Right? And the limit of u of t is 0 as t goes to x. Okay, again, you should be saying, what's he doing? It's the same thing. You said the same thing 3 times. Okay. Everybody okay? Right? You see what I'm doing? I let u of t be this thing. All I'm saying is that there's some number, and we define this function u of t to be this thing, and the limit of u of t is 0. Right? That's the same thing as being differentiable. Okay? Okay. Okay. Okay, so let me do one last thing. Actually, I'm going to use this. So I'm going to put a star on it. But I'm going to go one last. I'm going to make 1 or 2 more moves. So that's the same thing as that there exists f on t, u of t, such that f of t minus f of x equals f prime x t minus x. Plus u of t, t minus x, right? Right. And so let me actually just, instead of doing 2 small moves, 1 small move after another, I'm going to make 2 small moves at the same time. Where the limit of u of t is 0 as t approaches x. Okay. Okay, so what does differentiability mean? Differentiability means this, that you can express f as this thing, where this thing vanishes as you get closer to x. Right? As t gets close to x, right, you can express f of t in terms of this thing, where this thing goes to 0 as t gets close to x. Okay. What is this? Taylor expansion? Okay, that's good. There's another word for this expression here? I mean, Taylor expansion is
Slope.
so this is the
Linearization.
the linearization, right? This is the guy that whose graph is the linearization. The graph. What's the graph of the linearization? A line. What line? The tangent line. Thank you. Okay. So tangent line. Right? Tangent line. What does differentiability mean? Differentiability, that means that your function is basically a line, right? Your function is near x is basically a line, right? As you get closer to x, this thing vanishes, and you're left with the tangent line. Okay. Not only does it vanishes in a very fast way, right? This thing vanishes, this part vanishes, and this part also vanishes. It vanishes in a doubly quickly way, right? Even if we divided this error by t minus x, then it would still vanish. Okay. So it's not just vanishing; it's very much vanishing. Okay. So that's what you want to think of differentiability as, right? That your function is, basically a tangent line, basically a line. Right. So if you have some function, differentiability means that this function looks like it's differentiable. As I zoom in towards it, it becomes almost indistinguishable from a line, right? Right. Like the closer I get, it looks pretty much like a line, right? Other functions, right, not differentiable, and you notice that as I zoom in, right, it doesn't look like a line. Still doesn't look like a line, right? No matter how much I zoom in, it still doesn't look like a line, right? Okay. So that's what you want to think of differentiability as meaning. Okay. Okay, so now we're going to use this way of thinking. So properties of differentiability. Properties of differentiability. First, say I have some function f on AB. And f differentiable at x, some point in AB, implies that f is continuous at x. F differentiable implies that f is continuous at x. Okay. So I should comment that differentiability at one of these endpoints means that you approach x from the right-hand side or from the left-hand side, right? So instead of approaching x from either side, you're only allowed to approach it from the right-hand. Right? If I'm talking about differentiability at a, right? I'm going to only take my second points approaching from the right side of A. Okay, right? And if that limit exists, then we say it's differentiable. Okay. When I'm here, I'm only going to go from the left-hand side. Okay. So, okay, but okay. So let's this makes sense because if you're differentiable, then you're basically like a line, right? If you're like a line, then you're continuous. Okay. So that's how you want to think. The intuition about differentiable functions is typically goes like that. So you say, okay, we want to show that f is continuous. F is continuous at x. So let's just for simplicity let x be in the interior, so I don't have to worry about right and left. But you can fix it up if you want after class. Okay. So we want to show f is continuous at x. In other words, that the limit of f of x is f of c as x approaches c. Right. And let me write this as f of t as t approaches c. And I should write x, sorry, because I was saying continuous at x. Sorry. So the limit of f of t is f of x as t approaches x. Right? Okay. Okay. Well, why does that happen? Well, f differentiable at x, we just saw, says that f of t is this thing. Right? F of t is this thing. I'll call it double star. So by double star, we know that f of t is that thing, so it suffices to show that the limit of that thing is f of x, right? F of x plus f prime x t minus x plus u of t t minus x equals f of x. Right? Right? Well, it's true. Right? The end. Right? Because we already said that this thing goes to 0 as t goes to x. Right? So this thing goes to 0. What about this thing? This is a constant times t minus x. Right? As t goes to x, that becomes 0. Right? And so we end up with x. Right? As t goes to x, this vanishes and that vanishes, and so we get f of x. Right? So blah, 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 which is true. Which is true since the limit of u of t is 0 as t approaches x. Okay. Okay. Everybody all right? Any questions? Maybe I should have let you do it. Okay, so so other things that we're going to show. So now it's I'm afraid it's going to get a little bit dull, but we have to do it anyway. So that was kind of exciting, I think, but now it's going to be dull for a while. So yeah, okay. Anyway, just bear with it. So differentiation and arithmetic. So, okay, so I mean, you probably have seen some of these things before. So if f and g are differentiable at some x in a b, then the derivative of the sum is the sum of the derivatives. The derivative of the product. The derivative of the product is the first guy times the second guy plus the first guy times the derivative of the second guy. Right. Number 3, the derivative of a quotient is the bottom guy times the derivative of the top guy minus the top guy. Sorry, the derivative of the top guy times the bottom guy over the bottom guy squared. Okay. So the basic properties of differentiation. So, which one do you want to see? Which one do you want to see? Number 3? The last one? Okay, so let's... Okay, actually, let me do the... I'm going to do the second one and the third one, because the second one actually kind of illustrates a mathematical idea. So let me do the second one, and maybe the third one. Okay, so... let's look at the second one, right? So we want to consider the limit of f times g of t minus f times g of x over t minus x, as t approaches x. Okay, and we're hoping to get the first derivative times the second guy plus the first guy times the second derivative, the second guy's derivative. Excuse me. Okay, so so let me just write this out. F of t, g of t minus f of x, g of x, t minus x, as t approaches x. Okay, so I am going to throw in a, I'm going to do something funny. I'm going to subtract off a f of t, g of x, and I'm going to add it back on. F of t, I'm going to add on f of t, g of x. Okay, so I throw in a 0. I add 0, but it's a cleverly chosen 0. Okay, why do I add on that 0? Because I'm trying to get to the derivatives, right? I'm trying to get to the derivative of g, and I'm trying to get to the derivative of f, right? And you see that by adding in this factor, I sort of pull them out. So I know what's going to happen. Okay, so what happens? We can separate this. F of t, we get g of t minus g of x over t minus x. We also get g of x times f of t minus f of x over t minus x. Right? Okay. Well, what's the limit of this thing? Well, this is going to turn into g prime, right? G prime of x, right? This is g of x. This thing turns into f prime of x. Right? What about f of t? F of t. Well, it'll turn into f of x. How come? Because f is differentiable and thus continuous, right? We just showed differentiability implies continuity, so we get f of x. Okay, so that's the proof of that one. The proof of the next one is, the proof of the quotient one is sort of along the same lines. Do people still want to see it? Do people want to see it? I think it's probably better to go on. Yeah, if people feel passionately that they want to see it, it's not much harder than this. It just involves a little bit more algebra. Yeah. But basically, you sort of work in the other terms that you want, and then get what you want. It's not okay. Yeah. So notice that. So we are using a couple of facts here that were from the previous chapter, namely that if you have two functions and the limit, we're using the fact that if you have two functions, alpha, like a and b, right? And the limit of this is something, and the limit of this is something. Then the limit of the product is the product of the limits, right? The limit of the product, right? So if you have two functions, right? If one function goes to a and the other function goes to b, then the limit of the product. The limit of the product is going to be the product of the limits, right? So there was a theorem that we are using some theorems in here, right? Also that the limit of a sum is the sum of the limits, right? So there's there's a little bit of stuff going on underneath here. Okay. I don't want to. Let's not. Some of you may have saw this saw this already when you're in calculus classes. I think it's not really useful. Okay, let's do the chain rule, the chain rule, which is not particularly exciting either, but but at least it uses some of the machinery that we've just built. Okay. So the chain rule. So you have some function. You have some continuous function f. You have some function g, where the domain of g contains the image of f. So you can compose them. If f is differentiable at some x in AB, and g is differentiable at f of x, then g composed with f is differentiable at x. Right? You all know the statement of the chain rule. Right? And g composed with f, the derivative of that is g prime at f of x, f prime x. Okay, so the chain rule, you don't have to copy this down. Okay, so let's prove it. And the way we're going to prove it is using the idea that differentiability means that you're like a line. Okay, so here's the proof. So you want to show that the limit of g of f of t minus g of f of x over t minus x, as t approaches x, is g prime f of x, f prime x. Right? That's what the chain rule says. Okay. So say, okay, let's consider g of f of t minus g of f of x. Okay. So we say, well, look, this thing, we know that g is differentiable at f of x, right? So we can use the expression of this in terms of the tangent line, right? We say, okay, this is going to be f of t minus f of x, right? Remember, we have this thing that differentiable means that f of t minus f of x over t minus x is f prime x plus some function u of t, right? Differentiability at x means this. Okay. Differentiability of g at this point means that g of f of t minus g of f of x is going to be right, f of t minus f of x times this thing, right? Times this analogous thing, right? So we get g prime f of x plus some function of f of t. Right? Right? We haven't done anything. Just use the definition of differentiability. Okay. So now we're going to use the definition of differentiability again on the f, right? Well, right, f of t minus f of x, we know is going to be t minus x, right? T minus x times f prime x minus, I'm sorry, plus u of t, plus u of t. Right? Now we get this g prime f of x plus nu of f of t, v of f of t. That's a v, not a nu. Okay. Okay. So we just used our alternate characterization of differentiability 2 times. I feel like I've gone too fast. Have I gone too fast? Is everybody okay? Any questions? Any questions on what we're doing so far? Right. We want to show this is equal to that. Right? So let's look at the numerator. The numerator, we express it using the using this, using the definition of derivative, right? G is differentiable at f of x, that gives us this, right? F is differentiable at x, that gives us this, and that's it. Just use the definition of differentiability, the new definition, alternate definition of differentiability 2 times. So, right? So if we look at the g of f of t minus g of f of x over t minus x, well, that's just going to be this thing without the t minus x, right? So you get f prime x plus u of t, g prime f of x plus f v of f of t. Right? And then let t go to x. Right? As t goes to x, what happens? Well, u is going to go to 0, right? U will vanish, and t, as t goes to f of t goes to f of x, right? Well, v of f of t is going to vanish, right? As this term goes to f of x, v vanishes, right? So this vanishes and that vanishes, right? And we get what we want. We get g prime f of x, f prime x. Yeah.
So we have multiplied by the fraction f of t minus f of x over f of t minus f of x.
Where? We multiply by f of t minus f of x over f of t minus f of x?
Yeah, so, and then sort of separate it into 2 limits. One being g of f of t minus g of f of x over f of t minus f of x, the other being f of t minus f of x over t minus x. Would that be, like, would there be any problem with doing that?
I don't think so. I think that would also be okay. Let me, but. T go to x. I'm not 100% sure. Let me think. Talk with me later. Okay, so so we have 3 minutes. I think. Okay, let's stop here. Okay, yeah, there's no point in going on to the next section. So let's stop.